In this part we're going to simulate the filling of a tank with fluid. So in the beginning the tank is filled with air, and then we're going to have an inlet with water, and the water will come in here and fill this tank. If the tank is full, the water can come out through the outlet. So this will be a two-phase flow. And let's start with copying a tutorial. Enter your folder with OpenFOAM, tutorials, multi-phase flows, interfoam, and copy the dam brake tutorial. So I'm going to copy it to my desktop, rename it to lecture 4. Right, so let's clean up our folder, delete the all run file, delete this alpha 1. We're going to simulate it in a laminar. So we're going to simulate a laminar flow. So let's delete the k epsilon files, the new t, new tilde. So we just have our u, the static pressure, and alpha. Let's rename alpha to alpha 1. Alpha is the ratio between two fluids, so it's from 1 to 0. 0 means fluid 0 and 1 means fluid 1. So look in the constant folder. Let's delete the boundary file. Okay, system set field state. Alright, first of all, let's put in our geometry file. I already prepared a file. We're going to use the block mesher again. So open up the block mesh, and I'm going to open my case, tank filling. Okay, so you can just stop the video here and copy my geometry if you want to. So those are the vertices for the geometry I showed you a few minutes ago. We have 4 blocks, yeah, like I've shown you. We have an inlet, an outlet, our top and bottom walls, and front and back, which are empty. So let's save it. Let's go on. So we also have a file called G. This is the gravity force. It shows downwards in the y direction. So it's meters per square second minus 9.1 meters per square second. Yeah, transport properties. Those are the physics properties for our fluids. So phase 1 is water with 1000 kilograms per cubic meter, and this is the kinematic viscosity. And the second one is air with the kinematic viscosity like this, and this is our density rho, which is 1. So we'll leave the file as it is. And then we also have turbulence properties. Simulation type is laminar. I was in the wrong folder, I think. So our S model will be K epsilon, but turbulence, just turn it off. Save the file. Turbulence properties, simulation type laminar. Okay, I think we don't even need the file res properties, so we can just delete it. Okay, let's look at our boundary conditions. Just going to copy my file. So for alpha 1, which is our fluid distribution between the two faces, we have an internal field of uniform 0, which means our domain is filled with air. For the inlet, we have an inlet-outlet type, and water should come in, so it will be uniform 1 scalar. On the outlet, we have 0 gradient, top and bottom walls, 0 gradient, and front and back is empty. So just save it, and let's have a look at the velocity field. Yeah, the velocity, we'll start with a internal field with uniform 0 velocity. Our inlet is an inlet-outlet velocity inlet. The inlet value is 0.15 meters per second. For the outlet, we have a 0 gradient. The walls are no slip, so the velocity is 0 right next to the wall, and front and back is empty. Save it, and now the last file is our pressure, which looks like this in the beginning, but I'm going to copy my values and put them right in here. For the inlet, we have a 0 gradient. On the outlet, like you already know, uniform 0 pressure for the outlet, which is our reference pressure. Top and bottom walls are 0 gradient, front and back is empty, and in the beginning the whole field is uniformly 0. Save it. So let's look in our system file. The FV solution looks like this. Don't change anything, those settings are pretty fine. FV schemes, just leave them like they are. And the only thing we have to deal with is the control dict. So in the beginning it looks like this, but we need to change a couple of things. Let me just open up the file I already prepared. So the application will be interfoam. We're going to start from the start time 0, stop at end time, but end time will be 10 seconds. Our delta t will be 1 millisecond, but it will be variable this time, since we're going to use the Courant number to adjust the delta t. Yeah, right interval, we're going to choose like this, 10 milliseconds. Right compression, let's change it to compressed. Time format general, runtime modifiable, yes. Adjust time step on. This means the time step delta t will be adjusted according to a maximum Courant number. If you don't know what the Courant number is, just look it up on Google. But the Courant number is an indicator for the stability of our simulation. It should be below 1 to have a convergence in the solution. So to make it safe, we're going to use 0.5. And a maximum delta t of 1, but you can also delete it. Okay, so save the file. And I think we're ready to go now. We'll just open a new command line. Change our folder. Lecture 4. Type in block mesh. Check our mesh. Capital M. Check mesh. The mesh is okay. Then we're going to start our job, foam job, interfoam, and save our log file in log. Okay, now the simulation has started, and I'll be back in a couple of minutes to check our solution. Now our solution has been calculated, and we're going to visualize it in ParaView. I'm just going to open up a command line, change my directory, lecture 4, and execute the command parafoam. Okay, Make it full screen. Check PRGH and alpha 1 so we can visualize all the values we need. Okay, let's look at alpha 1. Alpha 1 is the proportion between air and water. And now let it play. So you can see here water coming in. And it falls down into the tank slowly. If you have a faster computer, the animation will be probably a little bit faster and more more fluent. So you can see all those waves here, and yeah, well, the tank will be filling now, and let's just enjoy our animation. What you can see pretty good is that all those air bubbles are going upwards because they have a lower density than water. So they're going upwards and just come out from the outlet. Okay, now 2 seconds are over, as you can see here. Now half of the tank is full, and it will keep getting fuller and fuller until the top is reached. I have to remind you that we have a laminar simulation, which is not really correct for this process since it's very turbulent, as you can see. So if you want to have correct results, which correspond to, you know, a correct physical process, you have to simulate it with turbulence. But for our case, just for demonstration purposes, it's sufficient to use a laminar case because you get a solution faster. Okay, now the top is reached. Here we have a few air bubbles. Okay, and now the tank is filled and water will go to the outlet now. And that's it, 5 seconds are over. We can wait to 10 seconds now, but I'm just going to skip it. Okay. In the end it will look like this. A little bit of air still in there, but the whole domain is filled with water now.